Hi class, today we are going to look at how fast computers really are when they are attacking passwords just through straight brute force. And they are so surprisingly fast that you'll understand why you need a good strong password to try to protect yourself against computers or hackers using computers to discover your password and then do whatever they want with that information if they are able to get into your accounts. Um, as you get older, it's just an inconvenience most of the time. They may lock you out of accounts. You may have to close bank accounts, and it's just problematic. Hackers don't really care if they get you or the next person. What they do is they find thousands of accounts that are vulnerable, and they just figure out which are the easiest ones to get into, and then they poke around in there and exploit whatever they can find. And so, really, you just want to be a little more secure than the next person so that you're not their target. Um, if you're ever in a position where you would be a specific target, you'd probably have to be like a high government official or something like that. And then you'll have teams of people helping protect you as well. So there is a tool that you're going to upload from Google Classroom so you can look at the code on what's happening. And this code basically just has a list of common words that we discovered in an assignment a while ago. And you can choose up to 3 different words to see how long it would take for the computer to guess just by going through the lists. There are a few caveats since this is a simple tool. You have to pick words that are on the list, and this is a list of 1,000 common words. There will be no spaces, no capitalization. You're not trying to trick the program here. All you're trying to do is see how fast computers really are. So when we open up a preview of the page, and feel free to go and mess around with the code if you want to change the visual aspects of this, change the CSS, that's totally fine. But if I'm just looking, say I have the password and it's cat, there are 2 methods. One is visual go, and what happens is you can see at the top that it's running through all of the words, and it's not finding the word cat. Let's try the word dog. Okay, so it found dog. Let me try one more time. It finds dog after 236 guesses and in 1.078 seconds. But the problem is when you see this visual up here, we look for password. That visual up there takes a lot of time because it's printing each word, then waiting a split second and printing another word. And that you'd never want to wait if you have a program that's going for this. I don't even know if password's in this list because it hasn't found it yet. So let's go to test. So it found test. Let me try one more time. Again, this is a pretty slow thing, and 870 guesses, it's 4 seconds. Now, if we do faster go, if we do the faster one instead of the visual one, it's not going to update at the top, so it doesn't look as fun, but so we know that test is 870 guesses in. If we hit faster go, 870 guesses without the visual is 0.002 seconds. And if we did dog, which is alphabetically earlier, faster go, 236 in 0.002 seconds. So basically the function call is what the delay is there. So we can then say dog if we wanted to have that. And I'm just going to do faster go, and it just did 235,471 guesses in 0.025 seconds. So, and then I'm going to ask you to add a third word, and that's going to take a little bit more time. So let's do dog. And this one's going to take a little more time. So you're going to see, ooh, okay. So computers do have a spot that was 6.2 seconds. And it was, how many, what is that? 235,705,706 guesses. And this is written in JavaScript, which is a relatively slow programming language, and it's still going. Those numbers are huge. So what you're going to do is you're going to do 3-word passwords, and you're going to do each test 3 times with different samples. You do have to pick words that are on the list, again, because this is just a simple demo. And then what I want you to do is you're going to go into Desmos Graphing Calculator, because we want to see how long would 4 or 5 words take. And it's going to take longer than you want to sit there waiting. So we're going to figure that out mathematically. So in Desmos graphing table, we can say, okay, we've got a table, and we're going to say we tried 1-word samples, then 2-word samples, and then 3-word samples. So we're going to put those in for our x's, and we're doing 3 trials of each. And the first one, it was like, say there were 0.005 seconds, 0.006 seconds, and 0.004 seconds. I'm making these numbers up. I want your actual numbers when you do this. For 2 words, it was like 0.01 or 0.001 second, 0.001 second, and say it was 0.002 seconds. And then for 3, say it was 6.2 seconds, 7.9 seconds, and 5.9 seconds. Which is significantly slower. Now 4 would take longer. Our tool doesn't even try to do 4 because it gets significantly longer. So we're going to mathematically look at this model. Now this is an exponential growth model. We could go into a math lesson to prove that it's exponential, but we're just going to be okay just saying, okay, this is exponential for this lesson, because this isn't supposed to be a full-out math lesson. So we're going to say y1 tilde e raised to the x1 power. And so that does a general curve of best fit. And it's not perfect. If we want, we could, let's just shift the graph around a little bit. Plus b. Yeah, that fits a little bit better. So you can put the plus b in or not, but the plus b does make it fit a little better. I think we could even put a plus c here, and that fits maybe even a little better at that point. 7, 8. Yeah, that's a better fit. It does say it's going to take. It doesn't really work when it's faster than this point here, because it's going into negative values, which aren't realistic, but it works pretty good. So then what we do is we can say, well, when x is 4 seconds, how long would it take? And this is saying it would take about 20 seconds. When x is 5 seconds, how long would it take? And then you just have to come up and find where is 5 seconds. That takes about a minute. Then you could try x equals 6 seconds. Or not 6 seconds, 6 words. And then you have to find out where do they meet up. And 6 seconds, all of a sudden, or 6 words, it's gonna really take off. I'm gonna do it without this, and we're gonna see 15 seconds, and then here's 116 seconds. So we just see that it starts to take longer and longer and longer. Now this is also limited. I want you to use real data when you're finding out these numbers, and then you're going to screenshot your Desmos work for the assignment. A few things to note: we are using JavaScript. We are also only using 1,000 words. The English language has way more words than that. When you start adding numbers there, you could make this list hundreds of thousands of words long, and it would be a more robust testing system, but it would take longer. So I just want you to see how exponential growth, it really starts to take longer and longer and longer. So the common rule right now is if you take 4 unique words that aren't common, like you're seeing in this list, it's going to be pretty safe from getting hacked. If you throw a number in with those 4 words, just somewhere in them, either between the words or somewhere in one of the words, that's even making it harder to get through, and that's pretty secure at that point. So I hope this is fun, and good luck.